mystery emerges in the Mariana Trench as scientists detect something below 11 kilometers.
Imagine standing on the edge of a world almost no human being has ever seen. Nearly 7 miles below the surface of the Pacific Ocean lies Challenger Deep, the deepest known place on Earth. It is a place so hostile that the pressure is strong enough to crush steel, and in more than 6 decades, only a handful of people have ever reached it. Yet the story of how humanity explored this hidden world is not one of constant progress. It is a story of extraordinary courage, decades of silence, and a return that changed everything. The story begins on January 23, 1960. On that day, Jacques Piccard and U.S. Navy Lieutenant Don Walsh climbed inside a small steel sphere known as the Trieste. Their destination was Challenger Deep, the lowest point of the Mariana Trench. As the submersible slowly disappeared beneath the waves, the two men began a descent that would last nearly 5 hours. Everything went according to plan until they were about 30,000 feet below the surface. Without warning, the outer window of the Trieste cracked. The entire submersible shuddered. At that depth, there were no rescue teams waiting nearby and no backup vehicle capable of reaching them. Turning around was barely an option, so they made the extraordinary decision to continue descending into the darkness. Hours later, the Trieste finally settled on the seafloor, 10,911 meters beneath the ocean's surface. Outside their tiny cabin, the crushing pressure was powerful enough to flatten a truck many times over. They remained there for only 20 minutes before the damaged window forced them to begin the long journey back to the surface. During those brief moments on the bottom, the crew reported seeing what appeared to be a flatfish resting on the seafloor. That single observation sparked a scientific debate that has continued for decades because many researchers believed no fish should have been able to survive under such extreme pressure. Their historic mission proved that human beings could reach the deepest place on Earth and survive. At the same time, it demonstrated just how close the expedition had come to ending in catastrophe. At Challenger Deep, a cracked window is not simply a damaged piece of glass. It represents the possibility of total structural failure within seconds. The two men who first saw the bottom of the ocean almost never returned to tell the story. Their near disaster shaped everything that followed. Instead of inspiring a wave of new expeditions, the Trieste's dive was followed by an extraordinary period of silence. For the next 52 years, no human being returned to Challenger Deep. Curiosity was never the problem. The real obstacles were engineering, cost, and risk. Designing a vehicle capable of surviving nearly 8 tons of pressure, pressing against every square inch of its hull, remains one of the greatest engineering challenges on Earth. Not long after its historic mission, the Trieste was retired, and building another deep-diving submersible would have required tens of millions of dollars with no guarantee that it would even survive its first attempt. At exactly the same time, another frontier had captured the world's imagination. The United States was investing enormous resources into the space race. The moon offered astronauts, television audiences, national pride, and a clearly defined objective. The deepest ocean offered none of those advantages. It was invisible to the public, unimaginably expensive to explore, and if something failed nearly 7 miles beneath the surface, no rescue mission could possibly reach the crew. As a result, government funding for crewed expeditions to the deepest trenches almost disappeared. Scientists continued exploring the oceans with robotic vehicles, gradually mapping ridges, hydrothermal vents, and shallower trenches. Yet the deepest point on the planet remained almost completely untouched by direct human observation. The silence was never caused by a lack of scientific interest. It existed because no one could justify the enormous expense and overwhelming danger of repeatedly visiting a place where a single failed seal or cracked window could instantly end an entire mission. For more than half a century, Challenger Deep waited in darkness. Then, unexpectedly, someone from outside the world of government science decided to return. In March 2012, filmmaker and explorer James Cameron climbed into a submersible unlike any that had come before. Called the Deep Sea Challenger, the vehicle had been developed largely through Cameron's own resources and private partnerships because few public agencies were willing to finance another attempt. Descending alone into Challenger Deep, Cameron became the first person to make a solo journey to the bottom of the Mariana Trench. Unlike the crew of the Trieste, he remained on the seafloor for nearly 3 hours, longer than anyone had ever stayed at that depth. During that time, he collected physical samples and captured high-definition footage of a world that had remained almost completely unseen for more than 50 years. The expedition represented far more than another record-breaking dive. It transformed one of Earth's least explored places into something scientists could finally examine in remarkable visual detail. Yet even with half a century of technological progress, the ocean reminded everyone that it still held the upper hand. During the descent, the Deep Sea Challenger developed hydraulic fluid leaks. They did not end the mission, but they served as a powerful reminder that the crushing pressure at Challenger Deep continues to expose weaknesses that engineers cannot always predict. Soon after its historic journey, the Deep Sea Challenger itself was largely retired from further deep dives. The pattern repeated once again. Someone proved the impossible could be done, the mission succeeded, and then the door quietly closed, leaving the deepest place on Earth waiting for whoever would dare to return next. The story of Challenger Deep did not end with James Cameron. In many ways, it followed a pattern that had already repeated itself once before. After completing his historic dive, the Deep Sea Challenger was largely retired from further expeditions. Once again, someone had proven that reaching the deepest place on Earth was possible. The mission succeeded. New footage was captured. Valuable samples were collected. And then, almost quietly, the door closed again. The reason had never changed. Operating a submersible capable of surviving nearly 7 miles beneath the ocean is brutally expensive. Every component must be constantly inspected, pressure tested, certified, and maintained. Even the smallest mechanical weakness can become catastrophic under the crushing pressure of Challenger Deep. Keeping such a vehicle operational for years is not only costly, it is genuinely dangerous. For a while, it seemed as though history was repeating itself. Then, another private expedition arrived, driven by an entirely different ambition. Its goal was not simply to reach Challenger Deep once, it was to reach the deepest point of every ocean on Earth. In 2019, businessman and explorer Victor Vescovo launched the 5 Deeps expedition, a privately funded project designed to visit the deepest location in all 5 of the world's oceans. At the heart of the expedition was a remarkable submersible known as the limiting factor. Unlike previous vehicles that completed a single historic dive before retirement, the limiting factor descended into Challenger Deep repeatedly. In just a few months, it completed more successful dives than the rest of human history had managed combined. At first, everything seemed routine. The mission collected water samples, sediment cores, and environmental data from depths greater than 10,400 meters inside the trench itself. These samples were sent to laboratories, where researchers began analyzing the genetic material they contained. No one expected the results. When scientists published their findings in the journal Microbiome in 2019, they described something that did not fit existing ideas about deep ocean ecosystems. Hidden inside the deepest waters on Earth were enormous populations of bacteria that specialize in breaking down hydrocarbons. These were the same kinds of microbes normally associated with cleaning up massive oil spills. Yet the concentrations found inside Challenger Deep were higher than anywhere else ever measured on Earth, higher than heavily polluted coastlines, higher than major oil spill sites, even higher than specially contaminated environments designed to encourage those microbes to grow. The researchers themselves admitted they had not expected anything like it. In their published paper, they described the discovery as shocking. The obvious question quickly followed. Where was all of that organic material coming from? Sunlight never reaches Challenger Deep. Plants cannot survive there. There were no visible oil reservoirs feeding the microbes. Some of the hydrocarbons could be explained by pollution that had slowly drifted downward from the surface over many decades. But the chemical fingerprints inside the sediment revealed something else as well. Some hydrocarbons appeared to originate naturally from within the trench itself. No one had a complete explanation. Suddenly, the deepest place on Earth was no longer simply a geological curiosity. It had become a biological mystery. And strangely enough, that would not be the only mystery waiting in the darkness. Around the same time, another expedition was reminded just how unforgiving the Mariana Trench can be. One research team deployed a deep ocean lander specially engineered to survive extreme pressure. It never came back. Somewhere during the descent, a tiny structural weakness gave way. The immense pressure crushed the vehicle in seconds before it could return a single piece of usable data. Months of preparation disappeared instantly. So did a significant portion of the expedition's budget. Incidents like this rarely make headlines, but among deep-sea researchers, they are an accepted reality. Equipment designed for the deepest ocean often returns damaged. Sometimes it never returns at all. Even today, after more than 60 years of technological progress, only a few dozen missions have successfully collected usable data from the deepest sections of the Mariana Trench, which stretches nearly 2,550 kilometers, roughly the distance between New York and Los Angeles. This constant risk explains why exploration advanced so slowly. Scientists never lost interest. The trench simply refused to forgive mistakes. Thousands of meters below the surface, there are no second chances. Yet while engineers struggled against pressure, another discovery was beginning to challenge something far more fundamental. It challenged one of biology's oldest assumptions. For generations, scientists had accepted a simple rule. Oxygen comes from photosynthesis. Photosynthesis requires sunlight. Whether produced by tiny phytoplankton floating near the ocean surface or by forests covering the continents, nearly all of Earth's oxygen depends on light. Without sunlight, new oxygen should not be produced. That idea seemed unquestionable. Then, in 2013, Professor Andrew Sweetman of the Scottish Association for Marine Science noticed something that made no sense. He was conducting experiments on the abyssal seafloor inside the Clarion-Clipperton Zone, approximately 4,000 meters beneath the Pacific Ocean. His team placed sealed chambers directly on the seabed and carefully monitored the oxygen trapped inside them. The expectation was straightforward. In complete darkness, microorganisms living inside the chambers should slowly consume the oxygen. As time passed, the oxygen concentration should steadily decrease. Instead, the exact opposite happened. The oxygen levels began rising. Not slightly, significantly. After 2 days, the amount of oxygen inside the chambers had climbed to more than 3 times the surrounding background level. Sweetman's first assumption was that his instruments had failed. The equipment was recalibrated. The experiment was repeated. The oxygen increased again. For nearly a decade, Sweetman continued testing the phenomenon, refining his methods and inviting other researchers to examine every possible source of error. No explanation made the mysterious oxygen disappear. Finally, in 2024, his team published their findings in Nature Geoscience. The evidence pointed toward an unexpected source. Scattered across the seafloor were countless potato-sized rocks known as polymetallic nodules. Rich in manganese, cobalt, nickel, and other metals, these nodules carried measurable electrical charges across their surfaces. Individual rocks produced voltages approaching 1 volt. For comparison, a standard AA battery operates at about 1.5 volts. In other words, these ordinary-looking rocks were naturally generating nearly 2/3 of the voltage of a household battery. Sweetman's team proposed an extraordinary possibility. Perhaps that electrical charge was powerful enough to split seawater into hydrogen and oxygen through a purely geological process. If correct, oxygen could be produced in complete darkness, without sunlight and without photosynthesis. No one had ever documented such a process occurring naturally on the deep ocean floor before. If the explanation proved correct, it would force scientists to rethink one of biology's oldest and most fundamental assumptions. If Professor Andrew Sweetman's explanation proved correct, it would force scientists to rethink one of biology's oldest assumptions. That possibility alone was enough to spark one of the most fascinating scientific debates of recent years. Almost immediately, researchers around the world began examining the findings. Some agreed that the oxygen measurements were extraordinary. Others questioned whether the proposed explanation was the right one. Was electricity flowing through polymetallic nodules really splitting seawater into hydrogen and oxygen? Or had something inside the experimental setup influenced the readings in a way no one had yet recognized? The questions multiplied faster than the answers. By 2026, the debate had become significant enough that Nature Geoscience published an editor's note explaining that parts of the original paper remained under continued review. Years after the discovery, no scientific consensus had emerged. Yet one important fact never disappeared. The measurements themselves remained. For nearly a decade, Sweetman and his colleagues had repeated the experiments over and over again. Independent scientists reviewed the methods, checked the instruments, and searched for errors. Despite all that scrutiny, no one had been able to fully explain the oxygen readings using the traditional rule that oxygen can only be produced through sunlight-driven photosynthesis. That unanswered question became the real story. Science has always advanced by investigating the moments when observations refuse to fit existing theories. Instead of closing the case, the mysterious oxygen readings encourage researchers to keep returning to the deep ocean, convinced that something important remained hidden beneath the darkness. Surprisingly, those unanswered questions reached far beyond Earth's oceans. They eventually attracted the attention of a space agency. At first glance, the connection seems almost impossible. What could the deepest trench on Earth possibly have in common with distant worlds orbiting other planets? The answer lies beneath thick layers of ice. Far from Earth, Jupiter's moon Europa and Saturn's moon Enceladus both hide enormous liquid oceans beneath frozen crusts. Sunlight never reaches those oceans, leaving them in permanent darkness. Yet Enceladus has already revealed an important clue. spacecraft have directly observed towering plumes of water vapor erupting through cracks in its icy shell, proving that its hidden ocean is actively interacting with the rocky interior below. Scientists believe Europa may behave in much the same way. Many researchers think both moons could contain hydrothermal systems on their sea floors, places where hot, mineral-rich water mixes with rock in complete darkness, remarkably similar to hydrothermal vents found deep within Earth's oceans. That similarity changed everything. Before sending future spacecraft to search those alien oceans for signs of life, NASA first needed to understand how life, oxygen, and chemical energy might exist in the darkest and most extreme marine environments available anywhere. Fortunately, one such environment already existed. It was here on Earth. Through a program known as Subsea, developed in partnership with NOAA and the Ocean Exploration Trust, NASA began studying underwater volcanoes, hydrothermal vents, and deep ocean environments whose pressure, chemistry, and geological conditions most closely resemble what scientists expect beneath the ice of Enceladus. The reasoning was simple. If future spacecraft are going to search for life hundreds of millions of miles away, scientists first need to know exactly what signs of life to look for. The best classroom for that mission is not another planet. It is Earth's own deep ocean. Suddenly, discoveries made nearly 7 miles beneath the Pacific Ocean took on an entirely new importance. The unusual hydrocarbon-eating bacteria discovered inside Challenger Deep, the unexplained oxygen appearing in complete darkness. Neither finding was simply an isolated curiosity anymore. Together, they became possible clues, templates that could help shape the instruments, experiments, and detection strategies carried aboard future missions, searching the hidden oceans of distant moons. Looking back across the entire story, a remarkable pattern begins to emerge. Everything started with 2 men descending into the unknown in 1960, a journey that nearly ended in disaster and discouraged further human exploration for more than half a century. For 52 years, Challenger Deep remained almost untouched, not because scientists lacked curiosity, but because the engineering challenges, financial costs, and overwhelming risks repeatedly outweighed the opportunity. Then a private filmmaker broke the silence in 2012, proving once again that humans could reach the deepest place on Earth. His vehicle, like the Trieste before it, was soon retired. A few years later, another privately funded expedition returned with biological discoveries that challenged existing ideas about life in the deepest ocean. Soon after, experiments thousands of kilometers away suggested that oxygen might be forming in complete darkness, forcing scientists to question one of biology's oldest assumptions. None of these events belong to science fiction. The discoveries involving hydrocarbon-consuming bacteria were published in Microbiome in 2019. The dark oxygen research appeared in Nature Geoscience in 2024, while scientific discussion and editorial review continue. NASA's interest in applying Earth's deepest ocean discoveries to future missions exploring Europa and Enceladus is documented through its Subsea research program. Every chapter of this story is built upon observations collected by trained researchers, measurements taken with calibrated instruments, and findings presented in peer-reviewed scientific journals. Even today, fewer than a handful of crewed missions have ever reached the very bottom of the Mariana Trench. The greatest obstacle was never a lack of curiosity. It was the extraordinary combination of cost, danger, and engineering difficulty that repeatedly forced humanity to look away. Yet each time someone returned, the trench revealed something unexpected.